Welcome everyone to our second time delay system webinar. We are really happy to see you here, and it's really nice to see the interest in these webinars. And today, this is my great pleasure to introduce Professor Miroslav Krstic. Professor Krstic is a professor at the University of California at San Diego, and he's an expert on many interesting topics, including input delay compensation, control of PD systems, and nonlinear and adaptive control. He has written a absolutely amazing number of books in these topics, so 16 books and about 400 journal papers. And he have received many prestigious prizes, including the Bellman Award, the Siam Reed Prize, the OSME Oldenburgen Medal, and many others, and member of many academies. And as a matter of fact, which is absolutely amazing, that not just being an excellent scientist, he's also an administrator. So he's taking a leadership position as the Senior Associate Vice Chancellor for research at UC San Diego. So I think without any further ado, I would give the floor to Professor Krstic, who today is going to talk about delay adaptive linear control. So Miroslav, the floor is yours.
Thank you so much, Gabor. I wish to thank both you and Wim for inviting me. I want to thank everybody for tuning in for this seminar. I've chosen a very simple, I've made a very simple choice for this lecture, and that is the choice to talk about results contained in the book that Yang and I published just last year with Princeton University Press. And I'll tell you more about him at the end of the talk. But before I start, I want to acknowledge three people who, as far as I can tell, none of them are here, but still important. The people who influenced me to start working on this topic, first and foremost, are Mirjan Jankovic, not on adaptive control delay systems, but on delay systems at all. After seeing his results on forwarding for systems with input delays, I decided that it was worth starting to turn the attention from PD control exclusively to delay systems. The second person whose results really caught my attention is Anu Anaswamy and her work from the mid to late 2000s on adaptive posicast control. And the third person, very significant to me, is Delphine Bresch-Pietri, who, as a visiting student in 2008 with me, for about a year, built in the initial bricks into the structure that ended up being this line of research and the book that I'm from which I'm going to present a few results. All right, so this is the outline of what I want to talk about. I have to start with a little bit of a refresher on predictor feedback in the non-adaptive case before I talk about its adaptive versions. Then I will talk about delay adaptive predictor feedback, both with the measurements of the transport PD state, which gives global results, and when the transport PD state is unmeasured, which precludes global results. All right, this is not a good sign, this freezing thing. Then I'll talk about problems in which the ODs parameters are unknown, and the OD state is unmeasured. And finally, I'll talk about an interesting and challenging case of systems with distributed delays, where both the delay and the kernel under the integral are unknown. All right, let me now give an overview, which is my perspective. Nobody knows the literature completely. I've spent enough time that I think I have a fair bit of understanding of what's been done in relation to predictor feedback. First of all, the Smith predictor is something that is the beginning of the field, but it's a different notion than everything else in this list. The Smith predictor works only for open loop stable systems. The zeros of the compensator cancel the poles of the plant, and it doesn't apply to unstable plants. To me, the key reference in all of this is a little paper by David Main that very few people know about, and he may not have come back to this topic ever again, but he published the first paper on predictor feedback. And I see that Peter Keynes is in the audience, and I didn't anticipate that at all. I've actually been on a mission to set the record straight on who invented this. It was not Manitius and Albrecht 10 years later. It was David Main. A very important little discovery. What they added later was a further perspective in terms of the spectrum being finite, or all but finitely many eigenvalues being at negative infinity. I'm sure they didn't know about David's paper, because David's paper was not even published in a control journal, but in an electronics journal. And then after that I'm gonna stop sliding this frame, because it keeps freezing my PDF here. So after that comes a paper by Kwon and Pearson in 1980, which introduces an idea of a transformation, which Zvi Arstein then formalized and considerably generalized. And this is now known as the reduction method, and only Arstein remains in memory in the literature in relation to this transformation. Finally, in 2008, while looking at cascades of transport PDs and ODs, Andres Michev and I came up with a control design based on backstepping. Not having looked at delays at all, but then after looking at what that feedback is, we realized that it's not new, that it's actually just a new way of deriving, and for the first time proving the Lyapunov stability of predictor feedback. So this is a brief history up until about a dozen years ago of this. There are other people who have contributed significantly, Watanabe and so on. There's work on robustness. I really apologize for skipping important work like Sabine Mondiez and a number of others in this history of basic milestones. Okay, so how does predictor feedback work? Let me focus on the simplest case. We'll remain linear in this whole talk. There is input delay. It's arbitrarily long. Ignoring it may and will result in closed loop stability, closed loop instability. And the invention, which again I find first in David Main's paper, is to use a predictor which happens to be, as written here, a way of expressing the future state using the variation of constants formula in terms of the current state and the past inputs. To us now, this looks trivial, but it's not. I mean, it's an idea that takes several elements. First, an element of thinking of using the current state as an initial condition. The second idea of recognizing that doing so will not result in any future inputs, but only the past inputs appearing in the formula. And the third idea, recognizing that that in fact is feedback, that it's not some kind of an open loop substitution for a future state, that one can talk about stability and robustness under all of this. So that's the design. Smishaev and I arrived at this from a different angle, from the angle of a cascade of a transport PD, which happens to be just an alternative representation of the delay. This is the frequency domain representation. This is the PD representation of the same thing. And applying backstepping, we derive the same feedback law. Here is the relation between the state of the transport PD and the delayed input. And there's not much more to say about that. Backstepping aspires to change the system using feedback transformations like in finite dimensional backstepping or in feedback linearization. Backstepping aspires to change the ODE, which you see here, contains an unstable matrix A, into a closed loop system that contains a stabilized system matrix A plus BK, and to turn this transport PD into a homogeneous transport PD, which is just a delay line fed by zero, which has not only exponential but finite time stability. So that's the ambitious idea of backstepping, and it is achieved using a backstepping transformation. The backstepping transformation is a Volterra transformation of the second kind of the state of the PD. You see that this transformation is the transformation of the lowercase u with itself. It's spatially causal. In the case of a transport PD, it's actually a spatial convolution transformation. There is the ODE state in addition to it, and the inverse of that, since it's a Volterra of the second kind, it's trivially invertible, and in this case explicitly invertible, and the explicit inverse from W back to U is given here. So looking now at the direct backstepping transformation, and aiming to change the system matrix from A to A plus BK, and aiming to assign zero at the boundary of the transport PD, one simply gets the predictor feedback, the one dating back to David Main's paper and Manitius and Albrot and Artstein and so on. So here is a summary of that, a block diagram. What I want to emphasize with this block diagram is that, yes, the feedback is at the bottom, but you will also see is two dynamical systems. One is the plant, the other is the partial differential equation. You can call it a delay, but it is a dynamical system. And what's in this feedback law is a full state feedback, a full state infinite dimensional feedback of the states X and lowercase u. And it is in that fashion that the stability of this should be studied. And it wasn't before that first paper by Smishaev and me that it was studied in, as a stability question. So here's the result: a summary of the plant and of the feedback applied at the boundary of that PD results in at least exponential stability in the norm of the states X and lowercase u. The norm on the PD state can be L2, can be higher norms, and so on. The first step would be to study it in terms of the L2 norm. The proof is based on the system transformed by the backstepping transformation. This system is a cascade of the stable, finite time stable transport PDW into an exponentially stable linear ODE. And the study of that is using the Lyapunov function that contains a sufficiently high weight on the PD state, which is autonomously stable. That weight is explicitly given here. And all of the coefficients in the estimate are calculated explicitly by the formulas given here. I'm just showing this not for the sake of full understanding, but just for the sake of the record that it's all calculated explicitly. It's not an existence result on stability. Let's now move into the actual subject of the talk, and that is adaptive control. Adaptive control already exists, and in adaptive control for 50 years prior to the beginning of this work on delay adaptive control, solutions have existed for plants whose parameters are unknown and whose states are unmeasured. So what is new in adaptive control of systems with delays, with input delays, is the case where the delay is unknown. So that is what I will focus on first, where everything else is unknown except the delay itself. But lots else can be unknown and uncertain. So in addition to the delay D being unknown, the parameters of the plant can be unknown, the state can be unmeasured, and the state of the transport PD can also be unmeasured. So in principle, by the end, and one can explore numerous combinations. You know, I haven't calculated how many possibilities are. I haven't calculated it recently. I think I did once in the first paper with Delphine. How many combinations of these uncertainties there are until the ultimate case where everything is uncertain and unknown, which was solved by Young. So anyway, one would in principle have to design one or more or all of these: an observer for the ODE, an observer for the delay state, an adaptive observer, a parameter estimator for the delay value, and parameter estimators for the ODE parameters. So here are the results in the literature for this situation with a discrete delay. As I said, there are several dozen possible combinations. We and others have not written several dozen papers on each of the possible combinations. Some combinations have turned out to contain challenges worthy of putting time into and publishing, and that subset is contained in this table. So the initial paper is this one by Delphine Brash-Pietri, where the main thing that is unknown is the delay. What I would say is the ultimate paper in this chain, in which everything is unknown, is this paper by Yang Zhu, with a distance of 8 years. And then all of this can be explored in the multi-input case. But when I say a multi-input case, it's important to appreciate something. The MIMO plants are very challenging in adaptive control, even without delays. And I'm not talking here the multi-input case where one has simply multiple inputs, but one has distinct delays on multiple inputs. And one has a situation where the system is not stabilizable using one of many inputs, but one has to employ multiple inputs to achieve stabilization. So these are not routine extensions. All right, so let me get back to that very first paper that begins the study, and maybe the most interesting of all the results. The paper on delay adaptive predictor feedback. So the delay D is unknown, and the problem is represented in such a way that it is linearly parameterized in the unknown delay. Remember, the transfer function of a delay is e to the minus ds. That's not linearly parameterized. It's when you go to the PDE representation that you can exploit and design an adaptive controller. In this situation, I assume that the transport state is measured. In many applications, such as those with a computational delay, this may not be true, but in physical systems where the delay is the result of a transport process whose convection speed is unknown, the full state would be available for measurement, such as in canals, for example, and in other circulation problems. So here are the two equations that I've shown earlier, the backstepping transformation and its inverse. And it's a certain equivalence version of those transformations, where there was D, now there is its estimate D hat, and there's nothing more to it. We simply replace that. That does create quite a bit of work and problems. Because once you differentiate this with respect to time, there's going to be d hat dot all over the place. So it's far from elementary to proceed. But the controller is certain equivalence. The controller doesn't change. It's the same one as it's basically a certain equivalence version of what you find in David Main's paper. So after a lot of work, which I'm skipping, the main design element is the update law. What's being updated is a scalar, an estimate of the delay. So what is this update law? This is maybe the most important slide in my whole talk. So let's concentrate on this fraction. That's the right-hand side of d hat dot. And there's certain assumptions. Gamma needs to be small enough, and so on. An upper bound needs to be known. Those are standard things. But let's concentrate on this. First of all, the denominator. Let me dispose of that. There is a normalization, and it's needed because of the certain equivalence nature of the feedback law. The normalization is by both the OD state and the backstepping transformation of the delay state. All right, so now the important stuff that I've highlighted in color. So this is an inner product of two quantities. The quantity in red is what you would always recognize in adaptive control feedback laws as the regulation error. This is what we are trying to drive to zero. When we drive W to zero, we drive U to zero, its inverse, also drive X to zero. What I show in green is what you would call a regressor. This is the quantity multiplied in the error system in the analysis by the parameter estimation error, D tilde, D minus D hat. So you see that this this is related to the form of the right-hand side of the plant, but this term actually appears on the right-hand side of the PD for W. That's how it happens to show up in the system. So what is the result? The result is a global stability result. And I'm emphasizing now that the state whose stability is being established is the state both of coming from the non-adaptive case with a plant state and the transport state, plus the state of the observer of the parameter estimation error. The upper bound, the right-hand side, is a class K function, a monotonically increasing continuous function. It is an exponentially increasing function, not by accident. It cannot be made better than that because of the unmatched nature of the unknown parameter relative to the input. There's a price of the adaptation transient, or the price of learning this D, and that's why there is such an exponential overshoot on the overall closed-loop system state. This is standard. If you force yourself to study your adaptive closed-loop systems as far as the analysis can take you, you can always get beyond the usual, the closed-loop system states are bounded or stuff like that characterizes early magnificent successes. It would typically be that you can get up to a bound like this. And in addition, the plant state, which was the whole purpose of the adaptive design, is regulated to 0, and the input as well. Let me now illustrate this on the simplest possible example one can think of. A first order example, which is unstable. And one can find that, for instance, in a paper by Alan Tannenbaum, and I forget, maybe Hitai Ozbai. It's been quite a few years since I've looked at where we pulled up that example. It was an unstable, highly maneuverable aircraft model. I think this was the pitch dynamics, and the important point here is that there is a significant instability and an even more significant length of delay, comparably long delay. In other words, you can't just pray that you'll luck out by ignoring the delay or by using a poor estimate of the delay if it's unknown. All right, here are the simulation results. I would say that maybe this is the second most important slide in my talk, or certainly the most important simulation slide in my talk. And there is a lot going on here. So it's a first order system. In the middle is the transient of the plant state. But it's what's on the left that is the most important, and that's the transient of the delay estimate. There are two curves here because these are two distinct simulations. One simulation starts, the true value of the delay is 1. One simulation starts from an initial estimate of delay 0. In other words, we assume and hope that there is no delay, and let the estimator figure out if there is some and how much. The other simulation is one where we start very pessimistically with a large initial delay value and see how it goes. So you see that the transient has been that both delay estimates end up on the average heading in the right direction. Not both of them quite get to the true value of the delay. One of them struggles a lot more gets quite confused. Both of them stabilize the plant. The one where the delay fluctuates a lot results in the state fluctuating a lot. And here is the input. Let me now zoom in on the timing here. So you see that the learning lasts, I will really round the numbers here. The learning, you can say, lasts about 3 seconds, 3 time units. Maybe you would disagree. Maybe you would say 4. Or you will say, no, it never ends. I'll say it goes for 3 minutes. So then how do I correlate that with the other pictures? Well, I see that after 3 seconds, the control, which has been going somewhat erratically, once the parameter has sort of settled, the control has settled into a non-adaptive controller, and you see its value going sort of exponentially towards 0. You also see in this plot that for the first 1 second, which is the value of the delay, the system grows exponentially in open loop because the input hasn't hit the plant. But once it hits the plant, once these values of the input start being fed into the plant, the tide turns and the stabilization begins. But this is nonlinear stabilization, simultaneous with learning. This is the big battle of adaptive control from 1 to 4 seconds, and it ends at 4 seconds. You also see a change in the control at about 1 second, and that is because it is at that time that the plant has begun to respond to the input. Okay, enough about that. That result is global, but the assumption that the transport PD state is measurable is too strong, and one has to look at the case where both D is unknown and the lowercase u is unmeasured. It needs to be estimated. So how would one estimate this lowercase u in red? Well, one would estimate it in a certain equivalence fashion. One would simply delay the values of the input on the basis of the estimates of the real-time estimates of the delay. That's what one feeds, and that's what one feeds into the backstepping transform and its inverse. The backstepping transform for the design, the inverse for the analysis, and the feedback law. So again, this is a certain equivalence version of David Main's feedback done with this delay adaptive observer of the delay. Here is the update law design at the end. You see that it's in fact almost the same as I've shown previously, with 2 differences. First, there is no normalization because there is no point in normalizing. Global stability cannot be achieved in this case. Normalization has a purpose when one aims for global stability. Why complicate the update law with an unnecessary normalization? Second, the differences are that the W and the U now come with hats because the measured U has been replaced by the estimated lowercase u. And here's the result. The result is local. Stability comes with an assumption that the norm of the initial condition is sufficiently small. I'll say what the initial condition in the state is in a second. So when the initial condition is small, then we have this local stability. there's no point in pursuing an exponential estimate because it's local. Therefore, linear is adequate. There's already weakening taking place here. There's nothing extra being paid here. What is the state of the closed loop system? It's all as before, plus not only the L2 norm of the estimate of the unmeasured transport PD, but also the H1 norm of that. We need both. And in addition to that, the regulation is achieved. What I want to stress the most is that the locality of this assumption imposes not only a smallness on the ODE state and on the transport PD state and on these observer states, but also on the observer error. So when I get back to this simulation test, you see that the initial delay estimate, I can no longer take it very far from the true value. I can take, when the true delay is 1.25, I can start from maybe 120, fairly close, at least for a plant that is aggressively open loop unstable. Let me now insert something that is the only thing that is nonlinear in this talk, and this is a combination of two results. A combination of a theoretical result by Delphine Bresch-Pietri from several years ago, extending our result for linear systems to general nonlinear plants, and the work by a current student of mine and of Payman Musavi at San Diego State University to tracking general nonlinear systems with an illustration on a robotic manipulator. In the interest of time, I'll skip these details. There is an appropriately designed update law. Let me just show you this. Let me show you the movie. This is an experiment. Even though it looks like a simulation, it's actually an animation of the experimental results which the manufacturer of this 7 degree of freedom Baxter robot provides as a capability. So you're going to see a successful maneuver of an arm of this robot under delay adaptive predictor feedback. The predictor is nonlinear. In other words, it's not explicit. It's also adaptive. I'm going to show you two experiments running in parallel. One without the compensation of the delay, which will be failing, and it's going to be in the upper right corner. So you're going to see this one shaking like a person inflicted by Parkinson's disease with uncompensated delay, and you're going to see this one smoothly move the arm from an initial position to another position. Just imagine a cup of tea being moved without spilling. So if you can look at both things, and the one in the upper right corner doing something stressful, while the one in the middle smoothly moving. The plot in the I'll run this one last time. So the plot here shows the real-time estimation of the delay. The delay is less than a second, plenty long to destabilize the feedback linearization control law that fails. but adaptively estimated to make the controller successful. Okay, so let me get back to my slides now. Okay, so let me now briefly talk about something vastly more general. Now I'm going to go to linear systems that require output feedback, linear systems whose state is unmeasured and whose parameters are also unknown. So a standard adaptive control formulation for systems given by a transfer function whose coefficients AI and BI are unknown. You know this formulation. We start with a representation of this system using the observer canonical form, and I've highlighted in red the coefficients of the denominator as they appear in the canonical form, and in blue the coefficients of the numerator as they appear in the canonical form. This is not for the faint of heart. It goes on for pages and pages and pages. I've taken a few, and bear with me, through half a dozen slides that are impossible really to digest. So I'll show you a few snapshots of what one has to work through to design a controller. So first of all, one needs to design an adaptive observer, and that adaptive observer we design using the so-called Kreiselmeyer or K filters. These are filters, stable filters of the measured output and of the input. These filters are designed in such a way that their non-adaptive version has an exponentially stable state estimation error. We're going to use their adaptive version, which is not exponentially decaying, but their non-adaptive version with a true theta gives us this. That's the idea of the design of these filters. There's similar filtering related to the reference signal, because now we're pursuing tracking, and I will not dwell on that. Finally, with these transformations, we arrive at a representation of the system whose dimension is equal to the relative degree of the plant. You see highlighted in red, in yellow, an integrator chain and a whole bunch of terms that contain uncertainties such as theta tilde, the parameter estimation error, and the parameter update rates. And for that, a controller needs to be designed, and it's not simple. For that, we employ the methodology from 1995 in that book. And that methodology results in a design given in this table. That again is standard. It's an application of what's in that book to this problem, appropriately set up for that design. At the end of the day, the real new thing is what's delay adaptive in it. And again, I emphasize the update law for the delay. There is an update law also for the parameter, for the OD parameter estimates, for those coefficients AI and BI of the transfer function. I won't dwell on that, but for the delay, it's again an inner product of the regulation error and of something that can be thought of as the regressor. Enough of that. Let me now go to my last subject, and that's distributed delays. So distributed delays are very interesting. It's unfortunate that I, at least, have not come across many applications that give models with distributed delays. But distributed delays are fascinating. Imagine that you have a system with an input even entering twice, undelayed and delayed. How confusing this is. Whatever you commit as your control design is going to hit the system twice, once as intended, and then a second time as unintended. And in the distributed delay problem, this is taken to a continuum extreme. This happens infinitely many times. The control, whatever control is being designed, is going to be hitting the system now and again and again and again, infinitely many times over the interval d, and it's going to be like that all the time. So it's a challenging class of systems. It's I would say a step above discrete delays in challenge. And for that class, again, there's a whole catalog of issues. The delay may be unknown, the delay kernel may be unknown, and all these other things may be unknown or unmeasured, as I spoke about earlier. So what results exist for this class of problems? The first result is actually by Nikos Bekeris-Liberis in 2013. And then further generalizations and extensions were developed by Yang. And then for the multi-input case, with multiple inputs, multiple integrals, multiple delays, and multiple kernel functions, again, by Yang, but first by Nikos in the non-adaptive case. So how is this problem solved? So let's focus only on the situation where the delay and the kernel B are unknown. Let everything else be known and measured. Everything else is even harder. This is hard enough, so let's focus on just this. So the approach to this goes by lumping together these separately appearing or bilinearly appearing unknowns D and the kernel function B of dx, lumping them together with the capital B being a vector, lumping them together and representing them component by component using these basis vectors E1 through En, and making the lowercase bi's the unknown scalar functions. So that's how the problem is reformulated and in principle over parameterized, because there's only there are potentially fewer unknowns in the original formulation. So it is for this system that we are designing a controller. And in the next slide, I'm going to use a compact notation, capital calligraphy B hat for this kernel function. So here's the design. The design is an adaptive certainty equivalence linear feedback law of the form KZ. First of all, what is Z? Those of you who are very familiar with the subject of predictive feedback, you know two things. One is that for discrete delays, the reduction approach and the backstepping approach result in the same thing. But you also know that for distributed delays, the reduction approach is something that is not subsumed by backstepping. Discrete delay is the reduction is subsumed, but for distributed delays is not. So what I'm showing you here as Z is essentially the Arnstein transformation, which eliminates the delay, and then for the resulting delay-free system, the feedback capital K is designed such that this closed loop matrix is made Hurwitz. And then all of this is done in a certain equivalence fashion with the adaptation. This is the design, just the update laws. So I'm showing you what really should be paid attention to in this slide are only two lines. One is the line tau D. This is the update law for the delay. The other line is tau BI. This is the update law for the delay, for the distributed delay kernels. I have spoken enough about update laws for the delay. I will not do that one more time. Let me talk now about what appears for the first time in the distributed delay design. That is how we update these functions. What are these functional update laws? So these functional update laws are infinite dimensional ODEs indexed by the spatial coefficient X. And what they include on their right-hand side, in addition to the usual and expected normalization, are products of the regulation errors. You see in red a regulation error of the Arnstein transformed plant state denoted by Z, and the backstepping transformed delay state denoted by W. So inner product of those with the regressors. And what are the regressors? It's the same quantity, FBI. FBI. It just occurs to me what that means when I read it out loud. So the FBI is nothing but the current state of the transportpedia, the location X. The result is as given here. In this case, it's local, and one achieves regulation. And finally, I don't want to finish this just with theory. I'm showing now simulations which come from the work that predates Yang-Zhu. This is the work by Nikos Bikaris Liberis. It's for known delay, but for the unknown kernel. The plant is scalar, but unstable, and you see this, considerable delay of instability reflect itself in the scalar plant rushing up until control finally imparts sufficient effect. This is the important slide that I want you to see. This is what at the end of the transients, the distributed the delay kernel function estimate B1 hat has converged to. So the unknown true B1 is actually a sine function, sinusoid function, partial sinusoid. This B1 hat has gotten close to it, but it doesn't have to fully estimate it. There isn't enough persistency of excitation in this scalar plant to fully estimate it. And thank God the transient hasn't been so bad to provide sufficient excitation for a perfect identification of this entire functional parameter. So this was a sneak peek into a whole library of results that exist in this book. And first of all, oops, I did something unintended. First of all, Who is its lead author, Yang Zhu? So this is Yang. He has worked on this material with me for 7 years, starting from his 2-year stay at UC San Diego beginning in 2013. Of course, a year worth of work by Delphine Bresch-Pietri preceded that and laid a foundation for Yang's further work. Yang is currently on the faculty of one of China's leading universities, Zhejiang University. And in this book, he has left little on the table in terms of unsolved delay adaptive control problems. Maybe, there are 2 things. One is that he hasn't considered problems with simultaneous delays on the input and on the state. One could look at the results from plants, backstepping designs for plants of that kind that Kharitonov published several years ago in a paper or 2. What's also completely underexplored are extensions of the one paper for nonlinear systems that Delphine and I published. So back to this book. What's up with the cover of this book? The cover art. So this is a painting by a Serbian artist by the name of Stojan Čelić, who actually used to be friends with Peter Kokotović back in the late 1950s. This is Čelić. He was the dean of the Academy of Art of the University of Belgrade and a member of the Serbian Academy of Sciences and Arts. And I happen to own this painting, and looking at it, I thought that its colors may not be a bad match with Princeton's black and orange color scheme in this series and in general, and that maybe geometric abstraction would not be a poor fit with the subject of this book. So with that, thank you so much for your attention, and I'd be happy to take questions.